My name is Zoltan Taracsak, and I'm going to mostly talk about the origin of volatile-rich magmas from El Hierro. I'm going to skip most of the evolution part. Let's get started. What are volatiles in magmatic systems? So these are a group of elements that prefer the gas phase over the melt, especially at low pressures. These include carbon, which dominantly is stored as CO2 in magmas, or various forms of sulfur, which will depend on oxidization state of the magma. For example, not SO4, but SO2, never mind. So sulfur dioxide or hydrogen sulfide. Hydrogen as form of water, mostly, and halogens like fluorine and chlorine. Generally, they are present in low concentrations, so around either below 1 weight% or 1,2 weight%. However, they strongly influence quite a few things in magmatic systems. For example, the physical properties of magmas, like viscosity, how the melt is formed, so for example, melting degree in the mantle, or how it evolves, for example, what kind of crystals form and in what order do they precipitate from a melt, and also the eruptive style of volcanoes, so effusive or explosive, not eruptive, that's a bad word. So yeah, they are quite important in magmatic system regardless of their low concentration. However, due to their low solubility at low pressures, they usually go through extensive degassing as the magma comes towards the surface. So the original volatile content is not represented by samples that we can collect on the surface. So we have to overcome this problem if we want to study volatiles. How can we study volatiles? We need something that is not degassed during this ascent to the surface, and one solution for this is to use melt inclusions. Now, melt inclusions are small droplets of melt that can be found. Go back. This is disappointing. So, melt inclusions are these small brown things, which are technically just small droplets of melt that are captured in crystals as crystals form during fractionation processes. They are quite useful as they are shielded from processes like degassing or by the host, and they will represent the volatile content of the magma at the time of trapping and at the pressure conditions of the trapping. Hence, the original volatile content of the magmas and the degassing path, depending on at which point these melt inclusions were entrapped in crystals, can be traced back and determined. There are some complications when we are using melt inclusions, though, which I have to highlight here. For example, the formation of these vapor bubbles, I don't know whether they can be seen here, but there are a few. There is one, which can be quite nicely seen. Because of these vapor bubbles formed, some of the volatiles, especially CO2, tends to dissolve into this bubble and go out from the melt inclusion itself. So this will cause us to underestimate the original CO2 concentration of magmas. Also, there is the problem of occasional crystallization after the entrapment. So it is possible to form, for example, small crystals, as you can see here, within melt inclusions, or we can form a small rim around the edge of the inclusion that will change its composition, both major, trace, and volatile element composition. Also, there is the issue of multi-phase entrapment, so it is possible to trap not just the melt phase, but also a gas phase together with it, which will cause us, if we also account for the bubbles volatile content, to overestimate magmatic volatile budgets. Now I'm going to move to the Canary Islands and El Hierro itself. The Canary Islands is made up of 7 volcanic islands, and most of them are still active. There have been 4 active islands in the last 500 years. The most recent eruption occurred in El Hierro, which I'm going to talk about. This is the westernmost, smallest, and youngest of the 7 islands. And the last eruption was in 2011-2012 at the southern tip of the island, around 300 meters underwater. And this is a very interesting eruption, especially in terms of volatiles. When melt inclusions were measured from these materials that were found floating around the Atlantic Ocean, it turned out that they contain extremely high concentrations of CO2 and sulfur. So as you can see on this diagram, there is around 3,000 and 3,500 ppm of CO2, also quite a lot of water, around 2.5%, and they also contained around 5,000 ppm of sulfur, which is quite high compared to other volcanic islands, for example, Hawaii. This eruption, which was a relatively small eruption, just around 0.3 cubic kilometer magma erupted on the ocean floor, emitted around 1.3, 2.1 megatons of CO2 and around 1.8, 2.9 megatons of sulfur, which is quite a lot compared to the size of the eruption. However, there is still an outstanding question whether this volatile-rich magma is typical to El Hierro or is just an outlier. To find this out, we had a look on melt inclusions from older, and by older I mean in the last 20,000 years, eruptions. And the short answer for this question, whether this was an outlier, is, well, whether this is the typical behavior, is yes, it is typical for El Hierro to produce such volatile-rich magmas, because what we found out after measuring quite a few melt inclusions for water, carbon, and sulfur concentrations, that the composition of the 2011-2012 eruption does overlap quite well with our samples, which are from the last 20,000 years or so. And we also measured one of the highest recorded CO2 and sulfur contents on oceanic islands up to date. So one of our melt inclusions where we only measured the glass, the carbon concentration was around 3,600 ppm, which is at the moment, as far as I know, one of the highest recorded in published literature at least. Because there are these vapor bubbles where CO2 can escape to, we also have to account for these, which can be measured by Raman spectrometry and determine the concentration of CO2 in those bubbles. And after reconstructing the CO2 concentration in melt inclusions, some of the inclusions contain up to 1 weight% carbon dioxide, which is quite a lot. So for example, 1 cubic meter of magma will contain around 28 kilograms of sulfur dioxide only. Also, the degassing path is very similar to the 2011-2012 eruption, which again confirms then that the last eruption is very typical of El Hierro's behavior. Now, there is another very interesting question. What causes this high volatile content in El Hierro? Well, we try to use trace element content of the melt inclusions, which can be used to narrow down the source of the volatiles. So in this diagram, you can see lanthanide-terbium ratios and lanthanide-yttrium and samarium-yttrium ratios, which usually stay quite constant as a magma evolves and produces crystals and such. So they can be used to trace back what was the trace element composition of the source. What was the trace element composition of the source? And we modeled a few melting paths where you assume original melt composition, for example, like the primitive mantle, which is just the mantle without the core. So we remove the core from the bulk earth composition, and then you get the primitive mantle. And using, for example, a primitive mantle composition, you can model El Hierro melt inclusions quite well. So they fall along a path with varying differences from it. Melting degree can be determined also. So for example, this point represents 1.5 degree melting, while this point represents 12 degree. And we can determine melting degrees of the source between 1 and 8%, around 8%. Which is quite a large range, but still lower again than Hawaii. So this is a quite low melting degree, which is typical on continental settings, but less typical in oceanic settings like El Hierro. A possible addition of subducted material in form of a possible addition of previously subducted oceanic crust in form of a silicate melt is possibly present, which are calculated in like these lines. So we can see that the composition of the inclusions do pull in this way. However, this is within error, I think, of the modeling. However, this melt addition from a subducted crustal material could account for volatile enrichment and could cause these magmas to be this volatile-rich altogether. Another interesting thing is looking at volatile trace element ratios, for example, carbon dioxide barium, water cerium, which I don't know why it's missing, chlorine, potassium, or fluorine neodymium ratios. These elements partition very similarly to each other, so their ratios should stay quite constant as the magma evolves again. Only one thing can change these ratios drastically, and that's degassing, because trace elements don't degas from the magma, so barium is not going to go into gas phase, however CO2 will. And if we look at the CO2 barium ratios on this diagram, we can see that even the most CO2-rich inclusions, where we accounted for the CO2 escape into the bubble, only just fall into the primitive mental estimates and only into the lowest, most conservative primitive mental carbon estimate. So it is possible, and we are quite confident, that CO2 degassing occurred even at mental depth, so up to 30 to 40 kilometers, which is quite important in that aspect, that when the magma is stored at this depth, the eruption is still possibly quite far away. However, if the gassing is already going on, you can detect CO2 on the surface as it will separate from the magma, and it is possible to detect as it gets to the surface through like multi-gas measurements. Another interesting thing to talk about is halogens, and these are these fluorine, neodymium, and chlorine potassium ratios. Fluorine neodymium ratios in the El Hierro melt inclusions are elevated compared to what we would expect in a primitive mantle. However, chlorine potassium ratios are more or less in the mantle range, which indicates that there must be something in the source that is quite rich in fluorine. And what could this be? This is most likely a recycled oceanic crustal component. And why I'm saying this, fluorine is quite easily recycled during subduction when an oceanic crust subducts at a subduction zone. However, most of the chlorine is lost during volatilization. And as Elliot talked about it before, and this is quite interesting because this is an indication of a recycled oceanic crust in the source through volatiles, which is quite rare. So the conclusions, that was really fast. El Hierro have been fed by similar magmas for the last 20,000 years, including the last 2011-2012 eruption. Magmas are extremely rich in both carbon and sulfur, hence potential subaerial eruptions, so some eruptions that doesn't happen underwater, but rather on the surface of the island, could have serious impacts on the environment, especially locally, maybe even globally if the eruption is large enough. Melt inclusions have variable trace element ratios, and based on these trace element ratios, we can suggest a primitive mantle-derived melt origin, and possibly a small amount of recycled crustal component in the source, a low melting degree compared to other oceanic islands, and volatile enrichment could originate from this recycled crustal component, indicated by the elevated fluorine neodymium ratios, and together with fluorine, carbon and sulfur could be present in this recycled component as well. However, this can be debated because we didn't find a very, very indicating proof that there is more carbon and sulfur in the source than it should be in a primitive mantle. However, we are planning to do isotopic measurements, especially from sulfur, so measure sulfur isotopes, which might help us to identify whether any recycled sulfur in the source mantle. And that's everything I wanted to talk about. Thank you very much.